In this video, we're going to learn about total eternal reflection. So far, we've learned about refraction and reflection. We've learned also about our refractive index. Now, this picture is very key and very important. Now, what does this picture say to you? I want you to take key points of every aspect here. Now, maybe you could call someone and look at this together, and I want you with your partner or by yourself, try and figure out why this picture is significant in terms of physics and refraction. So I want you to pause the video and spend 2 minutes writing out why you think this. Okay, so what is total eternal reflection? Well, first of all here, if we look at this picture, we're going from a high refractive index to a low refractive index. And look what happens as I change my angle. Here there's a difference of 7 degrees. Here there's a difference of 7 degrees, 12 degrees, and then 19 degrees. As I increase my angle, my refraction increases as well, and my variation of it increases. Till eventually I get a reflection instead of a refraction. So this is very important. In theory, this is how we use certain things as fiber optics and stuff like that, and telecommunications. Now, one thing that you must always notice is whenever we're doing fiber optics or total eternal reflection, we are going from a large index refraction into a smaller index refraction. Okay, so this is always the case. We're always going from a large to a smaller. It doesn't come the other way around. All right? Now, here's a little info bit. Diamonds, the cut of a diamond is almost just as important as the quality of the diamond. It is extremely important. Your best cuts will cost more money. It's what makes that sparkle. Now, this sparkle has to do with total eternal reflection. But there is a certain type of total eternal reflection that makes the darkle sparkle the best. This is called my critical angle. And we're going to learn about that here. So, when an angle of refraction is 90 degrees, the incident angle will have a value unique to the two media that form the interface. This unique angle of incidence is called a critical angle. For the light traveling from the medium with high refractive index to a medium with a low refractive index, the critical angle is determined by assuming the angle of refraction is 90 degrees. So, here's our first example. So in this example, we want to know what is the critical angle for quartz glass into the air interface. Well, there's a few things we're going to have to look at here. First, remember the light traveling from the higher index of refraction to the lower one. So it's always going from the high index to the lower. It's never going to go the other way. So even if I said air/quartz glass, I have to use my index 1, my N1 has to be the quartz glass, and my N2 is going to be the air, because it's starting in the quartz glass going to the air. It doesn't matter the order we're saying, we're always going from high to low. My second hint is this. So what we must remember for the angle of refraction to calculate the critical angle is it must be 90 degrees. So here we're going to have N1. So here we're going to have N1 is equal to 1.47 for refractive index. My refractive index of my second is equal to 1.00. Now we know my angle for my second angle is, my refractive angle is going to have to be 90 degrees. Okay, so the theta for the refractive is 90 degrees. Oops, not sine. Theta for the refractive is 90 degrees. We're trying to figure out at what angle the light must come out at. Okay, so what is the critical angle to create that 90 degrees for my incidence angle? So, let's look at this here. We know from Snell's law, if we go down here and we look, we know from Snell's law that we have my angle of incidence divided by my angle of refraction is equal to my refraction my refraction, sorry, index of my index of refraction of my refraction divided by my index of refraction by my original, so my quartz. So in this case here, we know this is sine 90, and sine 90 is always equal to 1, if you remember from Math 20, or even Math 10. So we know sine 90 is equal to 1, and that's my critical angle, so that's my refractive angle. So I know this here is equal to 1. So essentially, what we're trying to figure out is this angle here. So I'm just going to go theta is equal to arc sine, and we're going to have n2 divided by n1, which is equal to, and my n2 is 1 divided by 1.47, which ends up giving me a total of 42.9 degrees. Okay? So, now I want you to try these on your own just for a couple practice. So pause the video and do these 3 examples here. All right, now finally today, we're going to look at Newton and his colors. So before, people thought that prisms actually created these colors. They didn't think that, they thought that the prism changed the white light into these colors. They didn't think it was that these colors that we see here of the rainbow were in the white light. Newton had to prove that. And Snell's law goes farther into proving that. So what ends up happening here is the white light comes in, and then eventually we have these rainbows of colors. So I want you to think about this using Snell's laws. So look at these parts here with Snell's laws. So Snell's law explains all of this part here. What is always the same for each of these coming in? What changes for each of these coming in, and how will that affect everything else? So I'm going to give you 4 minutes to pause and be ready to explain this to me in class the next day. From your research and exploratory in your 4 minutes, hopefully you're able to look at a key thing that's changing for all of these colors is the wavelength. Now when we combine them all together, they're all going the same speed and they're all in this. But now as soon as they enter a different medium, the refractive index affects each wavelength differently. How so? Snell's law explains this very well. Now one thing you have to remember is all of these different types of wavelengths for each color. So these are some things that you do have to memorize for your tests. There are the wavelengths and their colors. Hopefully you'll have that on your posters already, the wavelengths, and that should be able to help you. Or you could always find it, if you know their frequency, you could always find the wavelengths in general by using the speed of light in air. So that's the end of this. I want you guys to do on page 683, questions 1 to 14.